Well, hello. Welcome back again, everybody. For this session, we have Cristian Klein talking to us about redundancy across data centers with Kubernetes, WireGuard, and Rook. And we know it's not always appropriate to run every workload in the public cloud, and we sometimes have to repatriate deployments to our own data centers. Of course, in doing this, we encounter a significant problem. How do we mimic the redundancy offered by the large-scale providers through such as availability zones? So I'm going to hand you over to Cristian now. He's going to take us away on this fabulous subject. Thank you, Cristian.
Thank you for the introduction. Hello, everyone. As Joy just presented, today I would like to share with you our experience in setting up a Kubernetes-based platform over multiple data center which works on any infrastructure. And at the end of my talk, you will understand the challenges and opportunities with using Kubernetes and cloud-native technologies to ensure that applications stay up, even if one of your data centers is taken down, for example, by extreme weather. A bit about me. I am a senior cloud architect at Elasticys and a researcher at Umeå University, both located in Sweden. I'm passionate about bridging the gap between those who speak data protection regulation on one end and those who speak cloud computing and DevOps on the other end. I am the architect of Compliant Kubernetes, which is an open source Kubernetes distribution. Compliant Kubernetes helps comply with GDPR, medical device regulations, and basically any ISO 27000 based data protection standard. We really care a lot about Kubernetes because any stability or security issue wakes us up at night and literally makes us lose sleep. So in brief, we offer a managed service so that customers can get the speed they want and the security they need. In what follows, I'm going to start with why. Specifically, I'm going to present how GDPR has moved very rapidly the IT industry from business as usual to you need to run in your jurisdiction now. Then I'm going to explain why it is challenging to set up a redundant Kubernetes platform on a typical EU cloud provider or on-prem. Next, I'm going to dive deep into the geeky part and explain the nitty-gritty details on how Kubernetes and cloud-native technologies can solve this problem. Finally, I'm going to present lesson learned and things you should be aware of before pressing the go button and adopting a similar solution. As the popular influencer Simon Sinek said, let's start with why. Now, to me, having to work with cool tech is already a good enough reason, so no need to find a better answer than that. But that's not what is really going to convince anyone to allocate budget to such a complex project. So let me give you a better why. In 2016, the EU adopted the General Data Protection Regulation, GDPR, and became a pioneer for protecting personal data. And at start, GDPR was largely ignored by the IT industry until it became enforceable in 2018, at which point it continued being ignored, until approximately summer 2020. That was a bit of a shock moment when the European Court of Justice ruled that the US Cloud Act is incompatible with GDPR. And those unfamiliar with the Cloud Act, it is a piece of US legislation which essentially allows the US government to force a US company to hand over personal data of EU citizens without really needing a reason. So basically, US favors national security, whereas the EU favors privacy. And as of today, there is really little will to reconcile these two disparate cultures around protection of personal data. So this begs more questions than it gives answers. Is it now geography or jurisdiction that matters? Can I, for example, use a data center located in the EU of a US cloud provider? And for better or worse, a French court ruling brought clarity in this case, and they pretty much said that it's really European jurisdiction that matters, not just geography. Okay, but what if we just use encryption? And that works, but the European Data Protection Board made it clear that the encryption keys must be outside US control. So that also kind of means that various cloud-based encryption keys, including custom-managed keys, are often deemed insufficient. And in fact, I saw at least Azure and Google publicly admitting that customer-managed encryption keys still allow accessing personal data via official channels. Now, I'm not sure how the situation looks like in your country. I'm pretty sure it looks differently from each EU country. But at least in Sweden, the Swedish public sector is pretty much not buying if a US cloud provider is involved anywhere in the supply chain. So needless to say, this is driving very much these EU cloud and on-prem solutions forward. Now, I empathize with the fact that not everybody is as passionate about regulations and legalese as I am, but let me try to convince you why you should care about the GDPR. And let me put it like this. The reason I get out of bed in the morning is that I want to build impactful applications. I want my work to be a small piece of a larger puzzle which makes healthcare and education better for society. However, in order to achieve that goal, we need society's trust. Otherwise, there is no need for you to bother on what feature to build next, because without trust, nobody will ever consider using your application to begin with. And just as an anecdote, I talked to a friend of mine who runs a psychiatry in Germany and asked her how she complies with data protection laws. And her answer was as simple as marvelous. I only take handwritten notes and store them in a safe. Yeah, no application, no digitalization, no nothing. And indeed, that is what happens if the public doesn't trust the IT industry. So to summarize this part, I see a trend in which there is more focus on data sovereignty and customers getting increasingly picky about who can get access to their data. And this in turn leads to higher demand for platforms that run either on-premise or on non-US clouds, or perhaps that can flexibly run on any cloud, on-prem, US, and EU clouds. A second trend that I noticed is focusing on extreme weather. Since the big European floods in summer 2021, I hear more demand for making sure that society-critical applications stay up, even if a flood takes a whole data center down. Like, it's okay for a data center to go down, but people don't really accept the fact that that makes them unable to access their healthcare application. And just the other day, as if to give me a concrete example and give me more fuel for having this presentation, somebody contacted me on LinkedIn and asked me how to meet these two demands, keeping data within a jurisdiction while tolerating extreme weather in the context of software medical devices. So I'm hoping that this presentation will give some inspiration on how to answer this challenge. Speaking of which, let me now explain why it is challenging to meet these demands when you don't know what infrastructure is thrown at you. First, let us keep in mind for whom we are building this platform for. So to me, it's really for the application developers. A platform should aim to maximize developer experience. Now, from what I've seen, a platform cannot fully make it transparent to the developer that their application is replicated. At the very least, the developers need to ensure that their application is stateless and the state is dealt with by purpose-built platform services like databases. However, developers are expecting the platform to make it easy for them to spread their application across data centers. And of course, since the application needs to be stateless, the platform itself needs to ensure that databases or message queues are properly spread and that they just work. Now, this sounds easier than done. And to understand why, we need to draw our attention to the infrastructure that is available below the platform. There are really two ways of exposing multiple data centers: availability zones and regions. In both cases, data centers are connected via low latency, high bandwidth network. And in both cases, they are geographically spread so as to reduce the risk of a major event, say a power outage, affecting both data centers or multiple data centers. However, when data centers are exposed as zones, they tend to have a single API. They tend to have a stretched private network, so you can connect your VMs via private IPv4. They tend to have a global load balancer, which allows to route traffic to any instance, any healthy data center. And sometimes they even have stretched block storage, but this is still rather rare. Now, in contrast, regions really feel like completely independent cloud providers. They lack a common private network, they lack a load balancer, and really, you cannot just have a load balancer that just works and routes traffic to the healthy data center. And here's now the core challenge that we are facing, and the core motivation for this project is that really when it comes to EU or on-prem clouds, they often lack availability zone. What they are presented as more resembles region. And the challenge is, does that stop us from creating an amazing developer experience? And of course, the answer is no, because otherwise I wouldn't be holding this particular talk. Thanks to cloud-native technologies such as Kubernetes, it is indeed possible to overcome the limitations of the infrastructure and create a platform which seamlessly spreads the application across regions. Now, let me remind you what cloud-native is. And I met many people that when I tell them cloud-native, they immediately think, but I asked for on-prem. Why do you tell this cloud thing now where I explicitly ask you for pretty much doing the opposite of cloud? So let me clarify this confusion. The definition of cloud native, part of which I reproduced on this slide, makes it very clear that these technologies are usable both in big public cloud providers and on-prem setups, which in their definition is called private clouds, as well as deployments that need both private and public clouds, called hybrid clouds in this particular definition. And this is not an ambition, but this definition is, the official definition that comes from the Cloud Native Computing Foundation itself, which is fostering an ecosystem of open source and vendor-neutral projects in the cloud native area. And in fact, I checked yesterday, and there are exactly 1,092 projects in the cloud native landscape. The Cloud Native Computing Foundation, CNCF, does an excellent job at classifying these projects based on their domain, such as observability versus databases versus container orchestrations. These projects also go regularly through a project maturity evaluation. So the CNCF puts them in a box called Sandbox, Incubating, and Graduated. And nowadays, there are even some end-user tech radar to classify these projects based on how mature are they perceived by end users based on end-user adoption. So with literally thousands of options, where does one even start? And in what follows, I would like to show you the choices that we have made, and hopefully that will give you a starting point, which can be easily adapted to your needs. However, big disclaimer, you might have to adjust the setup according to your particular needs and to your particular constraints. But that being said, I think it's a really good starting point for these kind of use cases. So here is the overall architecture diagram. In the middle, there is the application, which is the most precious asset that we need to take care of. It needs, of course, to be supported by some stateful services like a database. And then below the database are some low-level platform services, such as the stretched storage provider and a private network. And of course, these run on top of Kubernetes in order to maximize the portability from one cloud to another. Kubernetes, the way I like to explain to people, is kind of a bit like the power adapter of your laptop, so that you don't have to sell different laptops if you have different power plugs in the markets that you're addressing. And finally, on top of the diagram is the ingress. It's the stuff that directs traffic to a healthy replica of the application. Now, this is a lot of information to unpack. I understand that. So in what follows, I'm going to go through this diagram layer by layer and explain some of the intricacies and the choices that we have made. First, you need to choose at least 3 regions. This is very important. I noticed that some EU cloud providers, for example, they only have 2 regions that are close enough for being connected with high latency, high bandwidth, and low latency. And the reason why you need at least 3 regions is that 2 regions are really going to act as the active regions. They're going to need more computing and storage capacity, and they're going to do the heavy lifting and host application and its data. And these 2 regions really act a bit like the 2 hemispheres of a brain. The third region is really important, but it doesn't need to have that much capacity. It will only act as an arbiter to avoid split brain in case of a network partition. So what happens is that if you have a network partition between region 1 and 2, you want to avoid a situation where region 1 thinks that it's the active data center, that certain platform component needs to be the leader there. And then region 2 thinks that, well, I should be the leader since region 1 is down. So region 3, like I said, is acting as an arbiter, and it ensures quorum for platform components that need it. For example, like the etcd database that backs Kubernetes. Then, of course, you need to create VMs. And here, one important difference is that you tend to have one API per data center, and you have no stretched private network. So to overcome these challenges, we essentially used a public IPv4 addresses to all of the VMs. And then we configured Kubernetes control plane nodes in region 1, 2, 3. And the data plane nodes, we put them only in the active regions, in region 1 and 2. It is strongly recommended, but still kind of optional, to also have separate storage nodes. So you can also have that, to have like the storage nodes in region 1 and in region 2. And a very important consideration in this case is that since control plane and platform components are going to talk via public IPv4 addresses, it's very important to secure the nodes. Now, I understand that this is not like needs to happen, because let's not forget that etcd and Kubernetes and the kubelet and things like that, they are talking with something equivalent to MTLS. So there is usually something like a cluster certificate authority, which signs all the server certificates, and you have both authentication and encryption between platform components. But nevertheless, history shows that TLS is a rather large code base. It's rather difficult to get it right. There have been numerous attacks against the TLS stack. So I just sleep better at night by using security groups for additionally protecting these platform components and making sure that on top of MTLS, it's only really my nodes that can talk to each other. Once the VMs have been created, it's time to create a stretched Kubernetes cluster. To this end, we are big fans of the KubeSpray projects, and we even have contributions to it. In the grand scheme of things, KubeSpray is pretty much a very well thought through set of Ansible roles that at the end of the day sets up a production Kubernetes cluster. And some of the things that you need to take into account or to configure KubeSpray with are that you should taint the control plane nodes. And this is important because it improves stability and performance, right? If one of your application pods triggers out of memory, you're really sure that it won't take down the Kubernetes API server or whatnot. Then if you chose separate storage nodes, then you also need to taint and label them. So for those who are not familiar with the concepts of taints and labels, they are a really special way of marking nodes. And then you have tolerations on the pod sides so as to influence the scheduler on which nodes should which pods go through. But very important, you're just influencing the scheduler and you're not really making a one-to-one mapping like run this pod on this particular node. It's still the job of the Kubernetes scheduler to offer this flexibility and to take advantage of self-healing in order to make sure that if a node goes down, well, that pod is quickly restarted on a node that is reasonably similar. And finally, you want to add node topology labels. And this is really important because afterwards, this is pretty much what the application developers will use in order to spread their applications across data centers. And it will also, as I will show you soon, allow the storage cluster to understand the topology of the failure domains and make sure that data is replicated accordingly. I like to use here the zone label because it feels like we're essentially recreating zones here, even though technically the underlying infrastructure offers regions. And then, Kubernetes comes up with a standard set of topology labels that I strongly recommend to use. Now, one important consideration is that since often in these kind of deployments, you don't really know who owns the network between the data centers. Although the communication might be high bandwidth and low latency, it might still go a little bit via the public internet, or it might go via various providers. And GDPR really wants you to encrypt traffic over untrusted networks. So it's very important to also secure pod-to-pod communication between data centers. And to this end, we're using Calico as the container network interface. And Calico has recently gotten support for WireGuard, which is essentially a VPN solution in the Linux kernel, which can be used either for node-to-node or site-to-site VPN. And fortunately, Kubespray actually includes a configuration option, Calico WireGuard enable, which then tells Calico to use WireGuard, and then Calico then configures WireGuard accordingly. So you get pod-to-pod communication out of the box and with basically zero overhead. And I actually went as far as to do TCP dump on the network interface of each of the nodes. And you can immediately see that after enabling this option, the traffic is just not readable anymore. You cannot interpret it anymore. All this sounds great. So far, the developer gets a Kubernetes cluster across two data centers. Please remember that third data centers won't actually host the application, but will just act as an arbiter. The nodes have nice topology labels, which then can be used in Kubernetes deployments. And the developer also gets a private and, may I say, GDPR-friendly networking inside the cluster. And let's not forget also the cool things that Kubernetes come with. So you're also getting for free a private DNS server and also in-cluster load balancing, thanks to Kubernetes services. And this is really great because often EU cloud providers or on-prem don't have DNS servers that you can dynamically configure via an API to quickly add and remove services and help discoverability between application components or between an application component and database and so on. So all this sounds really nice so far, but we're still missing a solution for storage and for ingress. In order to tackle the stretched storage provider challenge, so first of all, why do we need to think about storage provider at all? And the thing is that since these disks are located on different data centers and we want to fulfill the persistent volume claims of pods, we need something that converts this set of random virtual machine disks into something that Kubernetes understands and can expose to the pods. And then there is a project called Ceph, which pretty much converts disks into a storage cluster. And then there is another project called Rook, which converts a Ceph cluster into a Kubernetes storage class, essentially. And if you configure these two, then essentially you get persistent volume claims that just work, and the data is replicated across the data centers, across the disk. Now, a very important consideration, as I'm showing here in the code snippets, is that Ceph really has two components, a bit like Kubernetes has its control plane and then it has its data plane. So the control plane is usually called the mons, and then the data plane is called the OSDs. And you need to make sure that the mons are sufficiently replicated. So recommendation is to have at least 5. And then you need to be very careful about configuring which are the active zones and which is the zone that will act as an arbiter, and configure it accordingly. And then when it comes to the Ceph data plane, you have the same consideration. You really need to configure Ceph to look at the zone topology label to understand that that's a failure domain and to make sure that it replicates data across the data centers. Because otherwise what would happen is that it would create 2 replicas of the same data, but then those 2 replicas might end up on 2 different nodes of the same data center. And that's not really what we want. We want those replicas to be located on 2 different data centers, so that if one data center goes down, Kubernetes can simply restore the pod on another data center, and persistent volume claims can just resume serving the data that the application expected. So not very complex, but needs a bit of attention to details. Finally, we need to somehow get traffic into the cluster. And this is really important because, well, we need to direct the users of the application to the healthy data center. And the challenge here is that EU and on-prem installations, EU clouds and on-prem installations generally lack what one would call a regional load balancer or a global balancer. And to tackle this challenge, we have several options. There is a project called MetalLB. So it's a little bit like a out-of-cluster load balancer for Kubernetes. And what it essentially does is that it does some BGP unicast magic in order to make sure that the ingress traffic is routed to the correct Kubernetes worker node. For those who are intimately familiar with MetalMB, yes, I'm aware that it also has an ARP mode, but that is not really useful when you want to replicate things across data centers. Now, the challenge with MetalLB is that it generally requires very deep integration with the cloud provider's network, which in my experience is rarely available. So just go ahead and call your data center provider today and ask them, hey, can I set up a BGP speaker with you? And you might not get quite the reaction that you would expect. It's available, but still rather rare. Now, the other option that you're having is to use some EU-based CDN, and there are quite a few solutions for that also available on the market. However, notice that CDNs like to decrypt to do TLS termination. So essentially, there would be one TLS session between the application users and the CDN, and then there will be another TLS session between the CDN and your Kubernetes cluster, respectively the application. And this pretty much means that the CDN can look at personal data since it decrypts and re-encrypts it. So you would need to sign a separate DPA, data protection agreement, with the CDN provider. And depending on where is your stance on this, you might or might not want to adopt that particular solution. Now, however, my favorite solution is DNS with health check that I'm going to talk about a little bit more in details in this slide. So when it comes to DNS with health check, in essence, this is pretty much a DNS provider that calls some kind of endpoint. If you're using Nginx ingress controller in your Kubernetes cluster, it already provides a /health endpoint, which returns 200 if everything is fine, and returns something like a 400 or a 500 if things are not fine and traffic should not be direct to that ingress controller. And then the DNS with health check regularly calls that endpoint and updates the DNS records accordingly with the healthy instances, with the healthy Kubernetes works, with the healthy Kubernetes worker nodes, which run an ingress controller that can then actually receive the traffic. And I have actually measured this, and depending on how you're configuring your DNS time to live and how often you're doing the health check, you can obtain failover between 1 and 5 minutes, which is fulfilling the requirements that we have met, and it's definitely way shorter than the time I need to get out of bed and to sit in front of the computer in case I get an alert at 2 a.m. So it's a win for the application user, and it's a win also for the poor administrator who needs to wake up in case the data center goes down. Now, an important consideration, I got this question quite often, is that IP addresses were ruled personal data in some European Court of Justice ruling. And of course, this came a little bit like a annoyance and shock to some people. Like, how can you say that IP addresses are personal data? They don't identify a person. But let's be very honest. They have been used to indirectly identify people and profile them for ad purposes. So, you cannot really fool legislators and a court around this. They were used to indirectly identify people, hence they are personal data. Fortunately, the authoritative DNS server does not get the user's IP address. So usually what happens is that you have a resolver DNS server in your internet service provider, in your ISP, and that one talks to the authoritative DNS server. Now, for those who are super familiar with DNS, yes, there is a so-called eDNS client subnet option in DNS requests, which reveals the IP address of the end user. However, this one is usually anonymized to a /24 network span subnet. So in that case, basically you cannot identify the user, and this has been ruled to be sufficient anonymization in order to not count as personal data. So this is great news, because this means that you can pretty much use any DNS provider, and all of them will be GDPR compliant since they don't process any personal data. So if you notice that, I don't know, one US big cloud provider has a service that you're familiar with and it's working great, then feel free to use that. We actually do that. So to recap, the developer gets a Kubernetes cluster with proper topology labels. They get secure pod-to-pod communication. They get a storage provider, which is replicated across data centers, and persistent volume claims just work. And they also get ingresses, so a proper ingress controller and a proper way to direct traffic. So far, so good. When I presented this to developers, they were saying pretty much like, wow, this is really cool, but I also need additional services. I need somewhere where to store my state. At the very least, I need a database. But if you could also take care of making sure that there is a message queue and maybe a key value in memory cache, that would be absolutely great. Okay, so at this moment, we need to stop and reflect, and we essentially have two choices. Either we come up for a solution for each of these services on how to replicate them across data centers, which has been done in the past and works great, but it does offer some complexity. Or we use Kubernetes operators. So for those unfamiliar, Kubernetes operators essentially create custom resource definitions, which are a way to extend the Kubernetes API. And then each of these operators comes with a service-specific operator, so one for databases, one for message queues, and so on. And that service-specific operator listens in on the Kubernetes API. And when you're defining a certain custom resource, then it basically just creates the right pods and right services and connects everything nicely so that the service is there. And this is really nice because it abstracts away the tedious and the boring parts of setting up a primary secondary replication with databases, or setting up 3 instances of a message queue and making sure that they are in quorum and things like that. And I'm really excited about this technology because that means that Kubernetes is not just a container orchestration engine, but it pretty much becomes an API standard around which the whole industry can share knowledge and standardize. We are using the Zalando Postgres operator for setting up a Postgres cluster. And in all of the following images, I'm going to show on the left side of the slide a snippet of the custom resource definition that you need to create. And on the right side, the architecture that you're getting and what features you're getting for free. So as you can see on the left side, it's a rather light definition, right? I'm essentially creating a Postgres resource. I'm specifying the size of the persistent volume claim. I'm saying how many instances there are, which version of Postgres. I can actually go deeper here and specify, for example, tolerations, so that I can create special nodes which are hosting only the database. And I can also, for example, set pod spread constraints to make sure that the Postgres cluster is spread across the data center or spread across hosts, depending on what you want to obtain. And with very little YAML, you get a lot for free. You get primary failover for free. For those who are curious, the Zalando operator comes with a component called Spilo, which through the Kubernetes API reuses the Raft algorithm in etcd for leader election. And that's how it decides which of the Postgres instances should be the primary and which one should be the secondary, and then just configures them accordingly. And it runs this control loop with a very high frequency. I think it's every 15 seconds by default. So it's really crazy fast at detecting if the primary has failed over and switching to a secondary. This operator also gives you for free point-in-time recovery, which is very important, right? If one of our developers has done a migration wrong and said drop table users, well, then you can very quickly recover the database to the state just before that SQL statement. And then, as I said, you can add resource limits, tolerations, and so on for proper capacity management and dedicating nodes to the database. And then if you're running a security hardened, or let me put differently, if you already have something like Prometheus to monitor the Kubernetes cluster, you pretty much also get monitoring for free. And then what we are also using is that we are setting audit logs on the Kubernetes API server. So which means that in case an application developer wants to access the database directly, this can happen, for example, for legitimate purposes, such as ad hoc analytics or for some very difficult migration steps. And in some regulated environments, you still want to keep an audit log and make sure that, well, you know who accessed the database at what point outside, let's say, the normal processes. And there is a similar operator also for setting up a Redis cluster. We like to use the one from Spotahome, but there are so many operators available there, so you have very high plethora of pick and choose. And it pretty much works as the Zalando operator. So you're using Redis Sentinels. Redis Sentinels is a bit like the Spilio of Postgres. So it's the component of Redis that decides which Redis instance should be the primary and which one should be the replica. And then you just configure a number of replicas and the number of Sentinels, and you're just getting high availability for free. Now, an important consideration is that Redis wants either 1 replica or 3 replicas for quorum. So in case you want to run Redis in your solution, then you might actually need 3 active regions. So you might need also a bit more capacity in the 3rd region in order to make sure that, well, you spread Redis nodes across data centers and avoid a split brain phenomenon at the Redis cluster level. And finally, RabbitMQ actually comes with its own operator as part of the open source solution. And similarly, you can configure it either with replica 1 if you don't need high availability. But of course, since the message queue, you kind of want high availability. So then you configure at least 3 replicas since RabbitMQ needs quorum. And then you also need to make sure that all 3 regions are active so that, and you need to add the right spread constraints so as to make sure that, well, Redis nodes end up on all of the data centers. So I'm really excited about this approach because just as HTTP is the hourglass waste of the internet, right? Below HTTP, you have a mess of various technologies such as IPv4, IPv6, wireless, wired, 5G technologies, whatnot. HTTP organizes all of these different network protocols, and then above you can have chatting, you can have video conferencing, you can have webinars, you can have email, and so on. So HTTP is reducing the complexity below in order to facilitate many more services on top. And in this particular configuration, Kubernetes acts like the hourglass waist of your platform, where below there is any messy, complex infrastructure, and then above you just have any kind of platform service and any containerized application that just works. And the other thing that I really like about this setup is that in case your organization grows large enough, you can have a nice separation of responsibilities. So I know that in small organizations, Kubernetes administrators are also doing database administration and also bit of backend development. But if you are growing beyond a particular size, then generally you want these roles to have clearly separated. And it's kind of nice that the system architecture also follows the separation of roles that you kind of naturally come up with. Alrighty. This sounds all too good to be true, right? I mean, so where is the catch? Let me discuss some of the pitfalls that we found with this architecture and things that you should be aware of before pushing the go button. Joel Spolsky, the former CEO of Stack Overflow, used to say in one of his blog posts, abstractions save us time working, but they don't save us time learning. And I'm really sure that if he had held this talk instead of me, he would have likely said, Kubernetes saves us time working, but it doesn't save us time learning. So the 3 really big things that you need to be concerned with when adopting a similar solution is really training, training, training. First, the network. The setup that I showed you is abstracting away the networking for the application developer, but somebody needs to understand how this network works. They need to understand how pod-to-pod communication works, where things are encrypted, where things are decrypted. They need to understand how ingress traffic works. And they really need to fully understand it in order to be able to debug it in the unlikely event where it doesn't work anymore. Second, Kubernetes is really a beast. There is a reason why we're having a certification, the Certified Kubernetes Administrator program, which is pretty large and pretty appreciated. And yeah, as I have shown you through the slide, subtle misconfigurations can have a huge impact on the stability and security of the platform. So make sure they get proper training in that. And finally, and most important, the storage and the database are really a beast. And these need to be specially considered because with some systems, you can just, oh, they don't work. Well, no worry. You just nuke them from orbit and redeploy from infrastructure as code or from whatnot. But when it comes to storage system, recovering them from backup can be extremely time-consuming, extremely stressful. So trust me, it's really scary when your storage cluster pretty much tells you, hey, I need your attention. If you see health warn in Ceph, that is not when you should be Googling for what does it mean low on available disk space. That's when you, out of muscle memory, should type the right commands to investigate what's happening. So initial training is just as important as keeping this training fresh in mind. And this leads me to my next point and my next gotcha. I strongly recommend to regularly test disaster recovery and resilience to failure. Now, you don't need to go overboard and have a chaos monkey that goes through your cluster and ruins everything. in my experience, it's just enough to stop the VMs from one data center, say every 3 months. And this ensures that your team is reasonably confident with the processes and the procedures and the resilience of the platform. And this also ensures that you catch subtle misconfigurations that perhaps application developers might be doing, such as forgetting using stateful sets when they should be using deployments, or forgetting to put pod topology spread constraints, as I showed in a code snippet, to really make sure that their application is spread. Let me summarize my talk. Data sovereignty and extreme weather are two trends which together demand cross-data center resilience on any cloud or on-prem. I hope I convinced you that cloud-native technologies can help you build a platform meeting these demands, and I have shown how to leverage projects like Kubernetes, Calico, WireGuard, Rook, and various Kubernetes operators to build this platform really quickly. And on the downside, each of these technologies saves time doing, but they don't save time learning. So make sure that you get the proper training before adapting the solution. Thank you very much for your attention, and I'm happy to take questions.
Well, Cristian, thank you very much. That was excellent. Again, fabulous overview for us there. And I love the tips on security groups over MTLS alone. All those pointers on Strat Kubernetes and Kubernetes operators. I think there's an awful lot for us to pick up there. Again, as you highlighted, this is an evolving area with the changes in legislation, etc. I've seen a number of dramatically react to this kind of circumstance. Are there any communities you'd highlight for people to keep in touch with or just check in with in terms of forums, to find out where people like yourself are pulling together these approaches that help us, deal with that kind of capability?
Unfortunately not. So I know quite a few forums which discuss data protection generally, and the Swedish Data Protection Agency, for example, is very active by their mailing list and their courses on making you aware of what are the latest developments. And of course, there are various forums to talk about Kubernetes and cloud-native technologies. And well, the DevOps Pro conference is also a premier forum where to discuss these things. There are also a conference called RedTech that kind of tries to talk a little bit about technology in regulated industry, but there's really a huge difference between those that speak regulation and those that speak Kubernetes, and there's not that many forums which try to bridge the two. I mean, I'm trying to do that via my LinkedIn post, so if people are interested in that, then please feel free to follow me. But otherwise, I would be very eager to see such a forum being created.
Yeah, sure, yeah. There's just some questions tipping in now in the last few minutes. What would be the drawbacks of using multi-region design with geolocation routing to the nearest region for your users?
So in our particular case, we were not required to do geolocation routing because the three data centers that we picked are rather closely geographical distance. So they're at less than 100 kilometers distance. Latency is below 1 millisecond. So you don't really care that much to which exact data center your traffic is located. Rather, you care about the fact that it gets to the healthy instance. And then another distinction from what the geolocation routing is usually trying to achieve is that in contrast to geolocation routing, where you kind of want to have the data as spread as possible, and then you want to direct the user to the closest replica of that data, essentially. Here, we're rather trying to keep data as grouped together in a certain geography and in a certain jurisdiction to really be able to point your finger, it's in this part of the map. So we haven't really been looking into geolocation routing.
No worries. Well, again, fabulous. Thank you so much. And I think, we should all be encouraged if people can reach out and get in contact with Cristian through his LinkedIn profile. I'm sure he can give us some more pointers, but that was an excellent session, Cristian. Thank you very much indeed.
Thank you so much for hosting this session, and thank you so much for the invitation.
Thank you. Bye all.
Bye.
See you in the next session after the break at 5 past the hour. Okay, thank you. Bye.
Thank you. Bye.